Right, so doing every challenge question from every Pearson textbook. This is part 2, book 1, chapter 2, the chapter about quadratics. Let's do this. Times this fraction by x over 2 over x over 2, and this by x over x, because of course you need a common denominator to add fractions together. So now we can just do this plus this and keep the denominators the same, which I believe makes this. X plus x is 2x, and the 2 on its own. We can cross multiply here to make this. Everything here, well, we can shove everything here onto one side first, and then everything here can be divided by 2. Now, the rest of this question is rendered completely trivial by the fact that you're allowed to use a calculator. If you desperately want to try and find a factorization, you can get it. And of course, because it says x is positive, the only solution is x equals 13. Cool. If you want to look cool, you can put this in a calculator, find the solutions, and then reverse engineer the factorization to make it appear as if you actually figured out that factorization. But if you do that, then whatever. Show the solutions of this or this. So this is a cheeky little proof of the quadratic formula that we're building towards. So okay, let's complete the square on this guy here. So, factorize out the a first, I guess, because I want a monic quadratic in here. I can complete the square now by halving this number and putting it in a square inside with x, like this. Half of 2b over a is just b over a. Imagine like halving 10 over 6, it's just 5 over 6, right? Just halve the top number. Take away the square of this thing here, as you always do when you complete the square. The square of b over a is b squared over a squared. Expand the a back out, and you get this. Of course, a cancels one of those a's to give you this. You can now do some little bit of rearranging here. This c is ca over a, and then this becomes b squared minus ca over a, or ac over a over here. It's absolutely fine either way you write that. Square root both sides to give you a plus or minus square root, and then bring the b over a over to the other side. Did I actually? Yeah, sorry, I'm being silly. Divide by a as well first. It's something I've forgotten there. Divide by a, and which gives you an a squared, and then when you square root, that goes back down to an a on the bottom, although it doesn't actually ask you to do that, so I guess that's fine. And then finally bring this thing over, and we end up with our proof here. Now, this is kind of interesting, the way that they've asked you to do this, and I don't really understand why they've asked you to do it this way, but that was a quadratic with an even coefficient in front of x. What about a quadratic that doesn't necessarily have that? Well, the easiest way to shift this, I guess, is just to replace this b with maybe a big B. Of course, that's not going to make a difference. And then just make the substitution 2b equals big B, because then I can just grab this solution that I've already got, rather than doing this from one from scratch. Just take the solution here, and just every time I see a b, replace it with a big B over 2. So that's what I'll do. So I've done that here. b over 2 squared is b squared over 4. I can then, and likewise over here, this 2 can go down to there. This 4, I could just sort of multiply top and bottom of this fraction inside the root by 4 to make b squared minus 4ac over 4a squared. And then, of course, when I root this, I can root the top and bottom separately. The root of 4a squared is 2a. And then these have the same denominators, so I can combine them together. And that's my solution as long as b is capital B, which is fine. I can put it back at the end. It's a dummy variable, isn't it? It doesn't matter what it is. And we're done with that question as well. 2g then. So prove that if you have a quadratic with some values a and c are given and non-zero, that this you can always pick a b such that this has distinct real roots. Now, quadratics have distinct real roots when b squared minus 4ac is greater than 0. And this isn't a proof because I can't be bothered to do it. But if you, no matter what you make a and c here, literally no matter what you make them, you can always just choose b to be massive and it would be fine. So, even if you choose a to be a million and c to be 3 trillion, just choose b to be a Google and this is completely fine. It will be bigger than 0. And if you choose a to be negative, which you're allowed to do apparently, then you're just adding stuff. So of course it's fine. And if you choose them both to be negative, it's as if you chose them both to be positive. So that's not a proof, but I can't be bothered to do a proof. I think it justifies itself. The math speaks for itself there. So I think we're done. Is it possible to choose a value of b such that source has equal roots, so b squared minus 4ac equals 0? Or if you just choose a to be that and c to be that, you'll very quickly realize that no, you can't, because you'll end up with this, which unless you want to choose b to be plus or minus 2i, you can't do. So that will be done with that. This one was kind of interesting, I guess. So we've got d equals this quadratic. So the 6 feet and the 14 feet, that's talking about the d here, and then the s is the speeds, that's these things here. So just substitute all of these 3 pieces of information into this quadratic here, and you get this. You can simplify all of them, and lots of you may never have solved a 3-dimensional simultaneous equation before. This one's actually pretty easy to do. All you have to do is take this equation and take away this one, because that removes these c's here, and you end up with this. And then take this equation and take away this one, which again removes the 2 c's, and you get this. And now you just have a normal simultaneous equation, which actually matches already. So just take this away from this, and you get this. Divide by 200, you get this. put that a value back into here to find a b, you get that, and then put that a and b value back into here, and you get c as that. And it doesn't end up being too bad. So now we've got our full equation here with a, b, and c with these known values. So I'll write that down. Skid mark of 20 feet long, so d is 20 here. Times everything by 100, I guess, is probably what I did. You can put the 2000 over here. Calculator will solve this for you in case you don't want to do it on your own. Apparently, I felt compelled to. I guess I don't really care. Of course, it's got to be a positive number, right? Because we're talking about distance. No, we're not. We're talking about speed, which is still got to be a positive number. So we're going to do the positive one here, and we're done as well. And finally, for chapter 2, we've got this here. Without loss of generality, I think we can just pick b to be 1 when we're doing this question here. So the ratio of a to b is the same as b to c. But I think I can just fix b to be some number, and and then a and c will just change to make it work. So I think that's fine. So just pick b is equal to 1, and then a few things happen. Firstly, 1 plus c is equal to a, based on this picture, and also based on these equivalencies here, where a to 1 is now the same as 1 to c, I can divide these through to get a over 1 equals 1 over c. And then I can cross multiply to get this, ac equals 1. And now this is just a simultaneous equation, right? So rearrange this to maybe be c is 1 over a, and shove it in here to get 1 over 1 plus a equals a. Times everything by a to get this, rearrange to get this. You can shove that in a calculator, or again, if you feel compelled to, you can actually solve this properly by doing all of this stuff. I've completed the square. Again, you could have used the formula that we proved 5 minutes ago. But anyway, I did this. This must be a positive number because these are all lengths. So it's going to be a half plus root 5 over 2, which of course is 1 plus root 5 over 2 if you just write it in as one fraction. B is also really interesting. It's just a good question. I'm going to color this section inside red. So all of this bit is red and this isn't. And the reason I'm going to do that is because I'm going to square both sides, which of course removes this square root and just puts the next squared over here. I can take away 1 from both sides to get this. And now look at this red object here. Because it goes on infinitely long, that's just the same as this original object, which I defined to be x. So all of this is just x. I've lost one of the root plus 1 pluses, but because it's infinitely long, that doesn't matter. So this is all just x here. And now we end up with the same quadratic we had before, which we know solves to 1 plus root 5 over 2. And we're done here. And yeah, chapter 3 will be next.